Modern physics is the foundation of our understanding of the universe, from the smallest particles to the largest cosmic structures. Because of its vast expanse, it is often difficult to learn because it covers a wide range of complex topics, from the counterintuitive principles of quantum mechanics to the mind-bending nature of relativity. These subjects require not only a solid understanding of advanced mathematics, but also the ability to think beyond everyday experiences. In this video, you will be learning all that is required to learn modern physics, from the very concept of physics to the mathematics that is required, and most importantly, the right choice of book that you need to select and read. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome on this topic, how to learn modern physics. First, let us understand what actually is modern physics, although there are different types of definitions, etc. But I would like to give you a comprehensive idea on the term and the deep understanding of modern physics. Well, when we talk of modern physics, it is actually denoting a certain timeline in history, certain discoveries, certain areas and events that took place for a certain period. So the historians and physicists marked it as the 20th century, what was developed onwards and greatly influenced by the early 20th century physics. So we can tell that it is a definition that modern physics is basically nothing but an effort to understand of the underlying processes of the interactions of matter using the tools of science and engineering. Now, as we are talking that what is modern, that talks of a specific time. So if we consider the timeline of the discoveries and innovations, then we can consider that which starts from around 1900 and goes up to 1920, but also certain physicists and mathematicians consider the discoveries of 1930 as well. Now, if we take this timeline of 1900 to 1930, around 20, 25, 30 plus years of discoveries, and if we can expand it, then it looks something like this. The first thing is that it starts with Planck's quantum hypothesis, and it started around 1900. And then what we do is that we find the typical Rutherford's atomic model, which is basically the first, model of atomic theory, which is still widely taught in the classes and colleges. And then comes 1905, the major breakthrough made by Einstein in his special theory of relativity. We also come around the same time, 1905, when a light of a certain frequency shines on a metal surface and it ejects electrons. This effect demonstrates that light between the particles, like photons with energy, is proportional to its frequency, and it is termed as photoelectric effect. After the Rutherford model, the main change that took place is Niels Bohr atomic model, and it says that electrons orbit the nucleus in fixed energy. Electrons can jump between levels by absorbing or emitting photons, explaining atomic spectra. So Bohr's model integrated quantum ideas with Rutherford's planetary model of the atom. After that, what we find is the major breakthrough in physics and science, which brought a total turnover, a total change in our understanding of space and time, which is Einstein's general theory of relativity, 1915. And then in 1924, which was proposed by Louis de Broglie, it suggests that particles like electrons exhibit both wave and particle-like properties, and this duality is basically a cornerstone or foundation in quantum mechanics. In 1925 came the Pauli exclusion principle, which states no two fermions, it's particles with half-integer spin, like electrons, can occupy the same quantum state simultaneously within an atom. Now, this principle explains electron configuration and the structure of the periodic table. After that, in 1926 came another important understanding, which is called the Schrödinger equation, the first non-relativistic equation, which says that kinetic energy plus potential energy equals to total energy. 1927 saw another rise of an important idea, which is called the Heisenberg's uncertainty principle, and it tells it is impossible to simultaneously know both the exact position and momentum of a particle with absolute precision. Well, the more precisely one is known, the less precise the other is, and this principle highlighted the fundamental limitation in terms of measuring what is called a quantum system. And after that came 1928, the Dirac equation, the first relativistic equation, which united special theory of relativity with quantum mechanics. I am making a series of videos which are called Beginner's Guide to Dirac Equation, which you can go ahead definitely and look into it. I've already made 3 videos and a live session where I'm trying to explain this extremely complex equation in an easy manner. So, what we can tell is that modern physics typically comes into play under extreme conditions. Remember that because quantum mechanical effects are extremely low and relativistic effects arises due to very high velocities and movements close to the speed of light. Now, once you understand this type of a timeline, you understand that what are the major discoveries, although there are certain areas which I have not covered between 24 to 25, and in between there are many discoveries, but overall this will give you that these are the areas which are primarily responsible in contributing modern physics. So can we look now into what are the major I would say physics concepts which leads to modern physics? Obviously, the first starts with dealing with the very small, the microscopic world, that is quantum mechanics. Then we move into the macroscopic world. I have mentioned is theories of relativity, because it comprises both special and general. Then we come to the very recent, a lot of discoveries are going on. I've already made a series of videos on quantum field theory, which you can check it on my channel Physics for Students, and the standard model of particle physics, where all these electrons, the bosons, the fermions, the Higgs, all are being united. And there is a very complex and a very big equation which is called the Lagrangian of the standard model, which almost takes a whiteboard, but there is a simpler version of that. I'm planning to make an equation on video on explaining what is that called the Lagrangian of standard model of particle physics. This standard model actually explains everything that we see around our world in terms of interaction. Then comes what is called the condensed matter physics, which immensely contributes to the modern electronics and several devices. Then comes the nuclear physics, followed by cosmology and astrophysics. There's a huge area of cosmology and astrophysics which is being covered, followed by thermodynamics and statistical mechanics, obviously, and finally this famous Richard Feynman's diagram, which shows quantum electrodynamics. Well, this is something which I'm going to explain later, because quantum field theory is one of the areas which quantum electrodynamics covers, how particles interact, how the annihilation and the interactions takes place. So with this gives you a pretty good idea of what are the areas, what are the fields, and how modern physics actually evolved. Now it is a good time that we should explore the very deep significance and the differences between classical and modern physics. Coming up into the next part of the video, what are the differences and relation between classical physics and modern physics? Now, in general, when we talk of physics, we talk of the macroscopic world or the physics in general. So classical physics overall, if we tell, then we talk of the speed of the objects which moves closer, lower than the speed of light. Obviously, the sizes are much greater than that of atoms, and there the energies and the speeds are relatively small. When we talk of the modern physics, we mean to say high velocities that are comparable to the speed of light, which is dealt in special relativity. We talk of very small distances, even smaller than that of the atoms and protons and neutrons, and there are very high energies which deals with the particle accelerators and etc. So this would give you a basic overall idea of what is classical physics and modern physics. However, this is a good time that we look into certain important significant factors of classical and modern physics. Now here you see, this is from Wikipedia. This gives you a nice idea about classical and modern physics. Remember, classical mechanics is something which is far less than 3 into 10 to the power 8. So you see the planets on the left hand sides. And then we come to quantum mechanics, which is less than 10 to the power minus 9 meters. That means very small. Then on the right hand side, it goes with the quantum field theory and the relativistic mechanics, where it is moving close to the speed of light. Now, one thing which I have not covered in this video, but I would like to make a point, is that some students and some people think that relativistic mechanics is equal to modern physics. No. Relativistic mechanics is something which is only related to relativity. It can be quantum relativistic equation, it can be special or general relativity equation, but relativistic physics and modern physics are not same. Because modern physics encompasses a huge area which we have just seen, and relativistic mechanics is only related to relativity. Let us look into the, I would say, the important aspects of classical and modern physics. If I talk of the application scale, definitely classical physics is applied to very slow moving objects which are a little bit bigger in size. Modern physics applies to microscopic, where speeds are extremely high and the sizes are extremely small. That is what I was telling, that speed and velocities are much less than the speed of light. Here it considers speed nearing to the speed of light, which are the relativistic effects. Gravity, most importantly, classical physics is defined by Newton's law of universal gravitation, and modern physics is defined by Einstein's special theory of relativity, where gravity is considered to be a manifestation of the space-time curvature. If I talk of from gravity, we move to the electromagnetic waves. This is defined by Maxwell's theory. Modern physics describe as both waves and particles, and quantum field theory takes it further. If I talk of the causality, then classical physics is very much which is deterministic in nature. However, modern physics, including Heisenberg's uncertainty principle, is highly probabilistic in nature. We can only find the probability of the particle given the likelihood where it can land into. Matter and particles here are treated as solid and indivisible objects. Here it is related to wave-particle duality, which can have both particle-like properties. This gives you a clear idea about what are classical and modern physics, and now it is the time to know the most important aspect, what kind of mathematics you need to know to learn modern physics. Now you already know certain area of mathematics, you really don't need to worry, because if you're studying classical physics, you already know them. In this part of the video, what I'm going to do is that I'm going to emphasize that apart from knowing the mathematics that you need to know to learn classical physics, what are the areas that you need to emphasize? What are the areas that you need to delve a little bit more deeper? And among them, the first thing which comes is linear algebra. This actually takes you into quantum physics, general relativity, everywhere. A good understanding of linear algebra. Next comes calculus, and in calculus I would like to emphasize more on partial differential equations, not the ODEs or so, because these are quite easy in terms of defining areas which are pretty simple in classical physics. Then comes what is called group theory. This would be important to know, understand Spinner's Dirac equation and the advanced concepts of quantum physics, and complex analysis, definitely for fractals or chaos theory, or even going into quantum mechanics, you need to know complex analysis. Apart from that, there are a few important things which is called tensor calculus. This is super important, because if you want to know general relativity, quantum mechanics, or you want to go into Maxwell's relativistic equation, everywhere you need to know tensor calculus. Then comes the Fourier analysis, which will be important for signals as well as understanding quantum physics. Probability statistics, obviously you already know, and variational calculus, this would be important to know the standard analysis part, followed by topology. Now, what I would like to also say is that if I go back to the first part, I've already made videos on how to learn this. That means what are the best books, etc. Linear algebra already there, calculus already there, complex analysis I have not made, group theory is also not yet done, but here tensor calculus and I would say probability statistics have already made certain videos, including topology, which is a very complicated subject in terms of understanding shapes and sizes. So you can very well go to my videos and playlist on physics for students, and if you want to know that how to study these mathematics, what are the books, what are the steps, you can find those books. So what we can tell is that these are basically the foundational tools. You cannot move into modern physics without knowing this. So a background in these areas will help you to understand the abstract and complex areas of modern physics, including quantum mechanics, general relativity, and the very new quantum field theory. So these are overall the mathematics for modern physics. If you want to go deeper into the mathematics, willing to learn the books, etc., you have already a lot of videos on my channel. Now we come to the central and the most important idea, that what are the best books in terms of what is the best book that you need to learn in modern physics. And in my prior videos I have already mentioned a lot of books in quantum mechanics, special relativity, GR, etc. But I'm not going to give you too much of options over here, because I have seen that too much of options might sometimes lead to problems. So I will just speak of a few books which will give you a comprehensive understanding. Now, this is a pretty old book called The Concepts of Modern Physics by Arthur Beezer, Shobit Mahajan and S. Rai Chaudhary. Now remember that you need to purchase or get hold of the 6th edition of the book. You might find the 1st or 2nd edition available on the internet, but that is not good. The global rating in terms of Amazon, it goes up to 60% with a 23% of 4-star, but soon I will show you how beautiful the book is arranged. Taking few of the reviews, you see that this is the best introductory books of modern physics. Then somebody tells good book but a little bit higher price. The books helps grow interest in physics. The book is good for modern physics and so on. So overall, when I went through the Amazon reviews, plus what I have personally read this book very well, that the review is very good. Nobody has said anything bad about this book. The author who has written this book, only one author I have selected, Dr. Arthur Beezer. Now, Dr. Beezer actually passed away last year on 2023 at the age of 92. And you can go ahead into the internet and study a little bit about Dr. Arthur Beezer. And he was born in Bronx on 16th of February and so on. So, very prolific author, distinguished faces, very well respected around the globe. Let us look into the content of the book. As you can see, it will first start, as I told, with special relativity, and then it will go into Doppler effect, length contractions, twin paradox, relativistic motion, etc. Now, all those appendix that are there in these books, it contains a lot of exercises, which I feel is good for any student to learn and do. Chapter 2 will be comprising of the particle properties of wave. So as I told you, the photoelectric effect, what is light, Compton effect, pair production, photons and gravity, everything is being covered. The 3rd and the 4th chapter basically talks about the atomic structure. So you can see that the nuclear atom, the energy levels and spectra, the phase and group velocities, partial diffraction, etc. are being covered. And then it moves into Schrodinger's wave equation, quantum number, and then the orbital quantum number. It now moves into what is called quantum physics. Further, if you look, it will contain all those periodic table, atomic structure, spin orbit coupling. Then it goes into chapter 8, the molecules, dealing with hydrogen molecules, etc. And then it covers chapter 9, statistical mechanics, statistical distributions, the Rayleigh-Jean formula, the Planck radiation, the black body part, and the free electron on metal. Now, one thing I would like to mention, this book particularly is not a specialized book. Don't expect that this book will teach you statistical mechanics or many electron atoms or probability or special relativity in too much of details. No, this is an overall book which will give you a complete idea of the entire spectrum of modern physics. So don't expect that each of the subjects will be dealt in details. So now we come to solid state mechanics. As you see, metallic bond, band theory of solids, etc. dealt with. Then it goes into nuclear structure, which are small nuclear properties, the binding energy, etc. And then it goes into nucleus transformation, which covers beta decay, gamma decay, cross section, and all of those. So if I talk of the overall idea of the book, I would say yes, this book is accessible to everybody. You just need to know a little bit of calculus. Second is that the biographical details, once you go through the book, it will give you the historical development, which I always emphasize is very good for a learner to know. It will start with relativity, which is easy to follow, and the first few chapters will make you ready before you go into Schrodinger equation. And you need to know a little bit of spherical coordinates, partial differential equations, and classical physics like system potentials, which I think you have already done, because otherwise, without knowing classical physics, how will you move to modern physics? So overall, this is a very, very good book. It's a little bit older book, I would say, but old is gold, so I would suggest you to go through this book. Excellent, well written, not much of mathematics is required. These three authors have taken their responsibility on their shoulders to teach you all the mathematics that is required. So yes, a solid understanding of classical mechanics will be required. Now coming to the next book, which is written by Kenneth S. Crane. This is called Modern Physics. It is an amazing book. Now you can see that the rating, although is 69%, this is fairly a heavy book. I mean to say the number of pages are more than 640. So as I always tell, that more the number of pages of the book, that means better are the explanation, hopefully. So this book also is an example. It is around 644 pages, which is quite a heavy and a thick book to carry. Now, talking about the review, it is all fantastic. Sher Singh and others, from Amazon, they have written at par or even better than Arthur Beeser's book. Now, you see, there's a comparison. I just talked about Arthur Beeser's book and its conceptual core of physics. I would recommend for each and every MSc Physics. So overall, yes, it is a very good book to read. Now about the author, this is Professor Kenneth Crane. He is a Professor Emeritus of Physics at the Oregon State University Department of Physics, and his current researches are these. You can go very well to his homepage, understand, read who he is, because I strongly suggest you need to know the author who is writing this book is objective before you go into this book. So this is Professor Kenneth Crane, who has written a superb, a gem of a book. Now before I go into the content of the book, here is an important note which I would like to show you, and please do read the red underlines. What is the objective of the book? Physics major, the course addresses two different audiences: physics major who will later take a more rigorous into quantum mechanics, etc., and for non-majors, that means people who are not doing a major, just they're doing for additional physics, that means that is also meant for you. So finding an increase for need for concept for modern physics. What are the prerequisites that the author assumes? You can read the last paragraph. Necessary prerequisites are standard calculus course covered in mechanics, electromagnetism, thermal physics and optics. These are already covered in classical mechanics. Calculus is used extensively, but no previous knowledge of differential equations, complex variables or partial derivatives are assumed. Now this is really wonderful. The author again takes up the entire responsibility to teach everything, and it is clearly written that calculus is used extensively, but no previous knowledge of differential equations, complex variables or partial derivatives assumed, although some familiarity with these topics will be helpful. So you can just pick it up and start reading. Let us see what are the contents covered in this book. First of all, it will again start with the failure of classical physics. This was not covered in Bayes' book. So you understand this part, Professor Crane make it clear that once limitation of a classical physics is reached, then you go into modern physics, special relativity, particle properties of electromagnetic radiation, then comes the wave-like properties, the Schrödinger equation and the Rutherford model of the atom. The next part of the book comprises of many electron atoms. So more or less the Bayes' book and this, the structure is more or less the same. The molecular structure, the statistical physics, all are being covered. Then comes the solid state physics, nuclear structure and radioactivity, followed by nuclear reactions and applications. So what I can tell about this book is that the elementary particles and a part of cosmology is also being covered. I don't remember, but Bayes' book doesn't cover much of cosmology. And then it goes into wave properties, Schrödinger equation, Rutherford model, molecular structure, statistical physics, and so on. So overall, these are the areas which are being covered. So the origin and the fate of the universe, the further into nuclear reactions, and then there are appendixes or exercises. So what I can talk about this book is that this book offers a very, very comprehensive overview of modern physics. It helps examples which are provided at the end of the chapter. It is very much recommended for self-study. If you really, really want to do a self-study, pick up this book of Dr. Crane, as he has already told that you don't need to know much about calculus. The second thing is that extensive use of calculus, but no prior knowledge is required, and Dr. Crane suggests that focusing on chapter 1 to 8 is the core material, and from 9 to 11 or 12 to 14 these are continuing chapters, with chapter 15 being optional. So what I can tell, both these books are absolute gem. There is no way you can say this book is better, that both have different styles, different ways of writing. Professor Crane's book is more or less for a self-study, a good recommendation for those who don't have any knowledge of, further mathematics, advanced mathematics you can take in. Same goes with the Arthur Beezer's, Shobhit Mahajan and S. Rai Chaudhury's book, Concept from Modern Physics. It is also mathematical, easy to understand, and it is an absolute, I would say, mandatory for those who wants to learn modern physics. So as I told you, I won't give you much of a recommendation. These two books are good enough, sufficient to give you a basic understanding of modern physics. So that's all for today's video. I'm immensely thankful for those who have taken up time for watching. Thank you for watching this video. If you've liked, please hit on the subscribe button and click on the bell icon of Physics for Students to get all the notification from this channel. You can write me to this email ID, and you can subscribe and like to my other channel, General Relativity Explained. You can follow me also on my Facebook, LinkedIn, Instagram and Twitter account. This is a very basic understanding of learning methods, books, mathematics of how to learn modern physics. Physics for Students will continue to surprise you with many surprising, fun-loving and beautiful videos on physics and mathematics. See you soon, but till then, may the good Lord be with you.